Hello everyone. So my name is Shravya. So the course that we are talking today is image and speech processing. Today's topic, what we will be talking about, is spatial filtering. So what actually is spatial filtering? Spatial filtering modifies an image by replacing the value of each pixel by a function of the values of the pixel as well as its neighbors. If the operation performed on the image on the pixels is linear, we call it as linear spatial filter. If the operations performed are called as non-linear functions, then we call it as non-linear spatial filters. What are the operations and which operations are called as linear filter are? First, they should satisfy homogeneity property. The other property which they have to satisfy is cumulative property. If these two properties are satisfied, then that operation is called as linear filter, linear operation. Mathematically, the operations which satisfy these two are the addition, subtraction, multiplication, division operations. If we want to talk about what is homogeneity property, then homogeneity property is, say suppose we have two variables a and b and two functions x and y. Then if we are performing some operation t, then t of a into x is equal to a into t of x. So this implies that if the operation performed on the new variable called a into x is same as the operation which is performed on x multiplied by the scalar a. When we talk about cumulative property, we can define it as t of ax plus by is equal to a into t of x plus b into t of y. So this is defined as if the operation performed on the combination of ax plus by new variable is equal to the scalar multiplied of the operation performed on x plus b times the scalar operation performed on the operation y. So if these two operations are satisfied, we call it as linear filters, and the operations and mathematically the operations which satisfy these equations are addition, subtraction, multiplication as well as division. The non-linear filters can be said as derivative, integrated, 0 to r, p of r, dr, Peter, like this. So these two can be called as the non-linear spatial filtering. If these operations are performed, then can be called as non-linear spatial filtering. Whereas if we are performing the mathematical operations like addition, subtraction, we can call it as linear spatial filtering. So first we would like to understand what is mechanics of the linear spatial filtering. In linear spatial filtering, we are performing sum of products operation between the image f and the filter kernel w. So we are considering that f is our image of size m cross n, and we have a kernel of size m cross n, small m small n. If kernel is an array of size, defines the neighborhood of the operation. So since we have the kernel w, there are two things which will define this kernel. One is size of the kernel, second is the coefficients that are existing in that kernel. So from this, the size will define the neighborhood of the operation, and the coefficients will define the nature of the filter. If the size of the filter that we are considering is 3 cross 3, then we consider 8 neighbors of our pixel. We consider the 8 neighbors of our pixels. If we consider the size of our kernel as 5 cross 5, then we consider the image So we consider our pixel and its 5 neighbors around each other about this pixel x comma y. The coefficients will define the nature of the filter. What are the different types of the filters that are available for us are low pass filter, high pass filter, third is band pass filter, fourth is band reject filters. So based on the coefficients, we will define the kernel is low pass filter or a high pass filter, band pass and band reject. The type of that filter that is required for filtering operation or this linear spatial filtering operation is dependent upon the applications. In simpler terms, we call the spatial filter as mask, template, window or simply a kernel. Mostly we prefer the word kernel for our analysis. Now let's consider an image which is represented here. We saying that this is our image. These are the pixels that are existing in our image. And we are considering a kernel of size 3 cross 3 here as shown here. So by default we are considering the origin of the filter is at the center, which is represented by W of 0, 0. We are considering, since our size of the filter is of the kernel is 3 cross 3, we are considering our 8 neighbors of our pixels. So if our pixel f of x comma y is our required pixel on which we are performing the filtering operation, then we are considering the 8 neighbors as shown here. So we can see that the filter is of 3 cross 3 size. The filter coefficients are represented by the W of 0, 0, W minus 1, 1, W minus 1, 0, so on and so forth. So this filter coefficients are represented by the positions W minus 1, 1, W minus 1, 0 and so on and so forth till W 1, 1. Here we are considering our image is also of size 3 cross 3 since our kernel is of 3 cross 3 size, and the 8 neighbors which are represented by f of x comma y, f of x comma x of x minus 1 into y minus 1, f of x minus 1 y, and then so on and so forth till f of x comma 1 y minus 1. So when we are performing the filtering operation, we are performing the sum of product of kernel coefficients and image intensities enclosed by the kernel. So the linear operation filtering is the sum of the product of the kernel coefficients and the image intensities enclosed by the kernel. Since we are considering 3 by 3, the intensities that are enclosed by the kernel are the 8 neighbors. So the intensities enclosed by the kernel are the 8 neighbors. We are saying that we are performing linear operation by sum of the product of the kernel coefficients and image intensity. So the product that we are performing is W of 0, 0 into f of x, y plus the product operations that are performed are W 0, 0 into f of x, y, W of minus 1, 0 into f of x minus 1, y, and so on and so forth. When we are performing the linear operation, we are assuming that the origins of the image and the origin of the kernel are mapped with each other. So, we are assuming the origin of the filter is mapped with the origin of our image. Since we are trying to calculate g of x, y, we are assuming that origin of the image is at f of x, y, and the origin of the kernel is present at f of 0, 0. So, when we place the kernel on our image, it can be represented as shown here. So, from there, we get the product terms as omega W of 0, 0 into f of x, y, W of minus 1, 0 into f of x minus 1, so on and so forth. The sum of all these terms will give us the value g of 0, 0, and it is the filtered response of the input image of pixel 0, 0. Right? So, if f of x is the pixel of our input image, the output image or the filtered response of the filter can be termed as sum of the product of the kernel coefficients and image pixels enclosed by the kernel, which is represented by g of x, y equal to omega minus 1, 1 into f of x minus 1 of y, 1 plus omega of minus 1, 0 into f of x minus 1, y plus so on and so forth till this equation, which can be simplified in terms of summations as g of x, y equal to sigma of s equal to minus a to a, sigma of t is equal to minus b to b, w of s, t into f of x plus s, y plus t. Now, the values of the s and t are ranging between a is equal to m minus 1 by 2, b is equal to n minus 1 by 2 for a 3 cross 3 or a m cross n size of the kernel. As the coordinates of x and y is varied, the center of the kernel moves from pixel to pixel to generate G image, the filtered image. If this means that if I have to calculate the filtered response of G of 0, z, then the origin of the kernel 0, z is mapped with f of 0, 0. If I have to calculate the value of g of 0, 1, then the origin of the kernel is mapped with pixel 0, 1. So, for every pixel, the kernel operation is performed. The sum of the product of the kernel coefficients as well as the image intensity values is performed, and the value of the filtered response is calculated. In our course, we are using odd size of the filter in both x and y directions. Since we are talking in terms of coordinate systems x and y, we are calling it as spatial filtering. We are calling it as spatial filtering, and spatial filter, the kernel size is of either 3 cross 3, 5 cross 5, 7 cross 7, so on and so forth. The mathematical operations, the mathematical equation which is used to represent the mathematical equation of the filtering, the operations that represent the mathematical equation of the filtering are correlation or convolution theorem, convolution process with 180 degrees rotated kernel. So we will consider how are these two operations performed. For simplicity, we'll start off with 1D equation of the filter equation. So that can be termed as g of x comma y, which is equal to g of x is equal to sigma of s is equal to minus a to a, w of s into f of x plus s, where a is ranging from m minus 1 by 2. So here we will consider first that our kernel is of 1D size, and the values are 1, 2, 4, 2, 8 as shown here, and the origin of the filter is at 4. I am considering my image f as 0, 0, 0, 1, 0, 0, 0, 0. And here I am considering my origin of my image is placed at the starting point 0 here. Now, as I said before, the filtering operation is performed when the origin of the kernel is placed or mapped with the origin of the image. So, it can be written as 0, 0, 0, 1, 0, 0 and 1, 2, 4, 2, 8. If we observe that these 1, 2 values here are not mapped with any values in my kernel, so the summation equation is undefined. To satisfy or to perform the summation operation, I am padding my image f with zeros before and after, so my summation can be done. So how many zeros are to be padded is decided by the size of the kernel. So if my size of my kernel here is specified as 1 cross 5, then the number of zeros to pad for our image f is equal to m minus 1 by 2. So in our example, we have the size of the kernel to be 1 cross 5. So our m value is 5. So the number of zeros that to be padded is m minus 1 by 2, which is equal to 5 minus 1 by 2, which is equal to 2 zeros. So before the image f, so this is our image f originally defined. We are padding 2 zeros before and after so that we can perform our summation operation with respect to our kernel. So if we pad zeros, we will try to calculate the sum of the product of the kernel coefficients as well as our image intensity values. So these can be defined as now here. So g of 0 is equal to summation of s is equal to minus a to a omega of s into f of x plus s. So g of 0 is given by 0 is given by S is equal to minus 2 to 2 omega S into f of S plus 0. Right? So this can be termed as the 1 into 0 plus 2 into 0 plus 4 into 0 plus 2 into 0 plus 8 into 0 plus 1 into 0, 0. So this can be calculated as 0. So we get G of 0 as 0. Now, when we want to calculate G of 1, we are shifting our kernel by one position towards the right. So, if we have to calculate the value G of 1, it can be said as sigma S is equal to minus 2 to 2 omega S into f of x f of S plus 1. So, we can calculate the values as shown here. The kernel is shifted one step towards right of my image. So, we get G of 1 is equal to 0 into 1, 0 into 1 plus 0 into 2 plus 0 into 4 plus 0 into 2 plus 1 into 8. So we get the value as 8. Similarly, we perform the operation to get G of, we get the value we perform the operations, the kernel operations, and we get similarly G of 1 is equal to 8, G of 2 is equal to 2, G of 3 is equal to 4, this G of 4 as 2, G of 5 as 1, G of 6 as 0, G of 7 as 0. So, the final correlation result is 0.824210. So, if we observe here, if my kernel is 12428, my correlated result of my between my image as well as my kernel here is the reverse of my kernel. So, if my image is having 1 at only single point and zeros at rest of the points, it is called as discrete unit impulse. So, if my image is of discrete unit impulse, if I do correlation with respect to a discrete unit impulse and a kernel W, then my correlated result is the reverse of my kernel. Now, we talked in my we talked about our correlation. Now let's talk about what is convolution. Convolution, as I said here before, is the similar to correlation, but my kernel is rotated by 180 degrees. So, we have consider the same equation, same example, where the kernel is 12428, which implies that 180 degrees rotated kernel is 82421, as we have written here. Now, I have my image F, which is a discrete unit impulse image. I have my discrete unit impulse and I am multiplying, I am doing my filtering operation with respect to a 180 degrees rotated W. Similarly, like my correlation process, I am going to pad my F with number of zeros, which is equal to m minus 1 by 2 number. So, which is turning up to be 2 in our example. So, I padded my zeros before as well as after my image and I am performing my convolution process. Now, if I am calculating my g of 0, I am getting it as 0 into 8 plus 0 into 2 plus 0 into 4 plus 0 into 2 plus 0 into 1, which is turning out to be 0. Similarly, if I want to calculate my g of 1, I am shifting my kernel one step towards my right side. So I am getting it as g of 1 is equal to 0 into 8 plus 0 into 2 plus 0 into 4 plus 0 into 2 plus 0 plus 1 into 1, which is turning up to be 1. So if I perform my g of 2, I am getting it as same 0 into 8 plus 0 into 2 plus 1 into 4 plus 0 into 2 plus 0 into 1, which is turning up to be 4. So if I perform my correlation result and calculate what is G0, G1, G2, so on and so forth till G7, I get my result as 0, 1, 2, 4, 2, 8, 0, 0. So if I observe the result here, if my image is of discrete unit impulse, I am multiplying by 180 degrees rotated of my kernel, I get my same kernel as my result, convolution result. Whereas for correlation, we have got the 180 degrees rotated result. So in these two processes, we are calculating the G0 or the filtered response by performing sum of the multi-product of the kernel as well as intensity values. So these two correlation and convolution processes can be termed as linear filtering. Linear filtering. Since we are performing in terms of x and y axis coordinate systems, we are calling it as linear spatial filtering. If our image is discrete unit impulse, then the one pixel which is having 1 pixels and rest all are 0, then the convolution result is same as the kernel, whereas the correlated result is the rotated version, 180 degrees rotated version of our kernel. Now, if we consider the same 1D correlation as well as the convolution which for 2D images, since our image is of size x comma y, we will consider the same operation to be for 2D operations. In our previous case, we have considered the size of the kernel to be 1 cross m and we have padded m minus 1 by 2 of zeros before the image and after the image. Here, since our size of my kernel will be m cross n, which is odd in size, then the number of zeros that has to be padded are m minus 1 by 2 for top and bottom and n minus 2 number of zeros for left and right of my image. Now, for example, we are considering a same discrete unit image where only at one point we have 1, for the rest of the points we have zeros. So, I am considering my kernel as 1, 2, 3, 4, 5, 6, 7, 8, 9, which is of size 3 cross 3. Right? Now, I am saying that my m is equal to 3, n is equal to 3. So, the number of zeros that have to be padded for f are equal to m minus 1 by 2, which is equal to 1 zeros top and bottom, n minus 1 as 3 minus 1 by 2, which is equal to 1 zeros left and right. So I get my padded image as 0, 0, 0 as shown here. Now, if I am doing my correlation operation, so I have to first map my origin of my kernel with my required pixel or the origin of my image. So my original image origin is at this point. So if I am mapping my origin of my kernel with respect to the origin of my image, I place my kernel as shown here. So if I have to calculate my g of 0, 0, I get as 1 into 0 plus 2 into 0 plus 3 into 0 plus 4 into 0 plus 5 into 0 plus 6 into 0 plus 7 into 0 plus 8 into 0 plus 9 into 0, which is turning out to be 0. Similarly, if I have to calculate the value g of 0, 1, I shift my kernel one position towards my right. So, and I continue the same process as discussed for g of 0, 0. So, I get my 0, 1 as 0. So, 0 of 0, 2 as 0, so on and so forth. Okay. Now, I am shifting if I want to calculate my value g of 1, 0, then I am shifting my kernel towards down by one step and I will calculate my values. So, which can be calculated as 1 into 0 plus 2 into 0 plus 3 into 0 plus 4 into 0 plus 5 into 0 plus 6 into 0 plus 7 into 0 plus 8 into 0 and 9 into 1. So, this 9 value, when we shift down by one step, this 9 is mapped with 1. So, when we do the product operation, we get 9 into 1, which is equal to 9. So, we get the value as 9. Similarly, we do the correlation process by shifting one step to the right, then one step to the bottom, and we get the correlated result for the 2D image as shown here. So, what we have discussed before is very similar. If we have a discrete unit image and we are trying to do the sum of product operation with respect to our kernel, we get the 180 degrees rotated version of our kernel. So, now, if we consider for convolution, the process is the same, where we are padding our f with number of zeros as m minus 1 by 2, n minus 1 by 2, m minus 1 number of times as the top and bottom, and n minus number of zeros for the left and right. Now, when we are considering convolution, we will consider the 180 degrees rotated version of our kernel. So, we will map our origin of my kernel with respect to the first pixel or the origin of my image f. So, I get my g of 0, 0 to be 0, g of 0, 1, 1, so on and so forth, 0, 4. So, similarly, when I want to calculate the value of g of 1, 0, I shift my kernel by one step. I map my 1 with respect to the 1 of my image. So, I get g of 1, 0 as 1. So, similarly, g of 1, 1 will give us 2. So, g of 1, 2 as 3, so on and so forth. So, when I am doing convolution of my image as well as my kernel, I get my same result, same image or the same output, which is the kernel. So, in correlation, I get my 180 degrees rotated version of my kernel. Right? So, from the above examples, we can conclude that both correlation and convolution are performing the sum of the product in kernel and of the image, both in 1D as well as in 2D. So, they can be called as linear filtering. Among these two, which operation is the best? for consideration for linear spatial filtering, whether we should perform correlation or convolution can be decided by the properties of these operations. The properties that we will consider are commutative, associative, and distributive functions. So, if we consider for convolution is both commutative, associative as well as distributive property. But when it comes to correlation, we observe that correlation is not as commutative, not associative, it is only having the distributive property. So, when we say that linear spatial filtering is operated or spatial filtering operation is performed, then we consider that convolution operation is done. That means we calculate the 180 degrees rotated version of our kernel, do the sum of the product operation and get our output filtered image. So, we have considered the convolution as our basic operation that is performed when we are considering for our output filter image. So, when we consider the types of the spatial filtering, as I said, we will have low pass, high pass, band pass, band reject. So for now, we will talk about the low pass spatial filtering, which can be termed as otherwise smoothing spatial filtering. Why do we use smoothing spatial filter is reduce the sharp transitions in our intensities. So where do we use these filters? So we use in noise reduction. Why do we use it in noise reduction is when image is there, we have an image and there is a noise introduced for that image. Because of the noise, the intensity will have a random increase in our intensity. So since it is a random noise, we will have a random increase in our intensity values, which can be termed as sharp transitions in the intensities. So these can be reduced for using smoothing filter. So because of this, we get our noise reduction. Since noise reduction is achieved, we can use it for aliasing before decompressing or at the receiver side. Before we perform our operations on the decode our image or decompress our image, we perform this smoothing operation to reduce the aliasing property. Then, using smoothing filters, the sharp transitions are reduced, because of which the irrelevant data can also be reduced. Because of irrelevant data, we can even detect reduce the false contours and smoothen them and convert into a required image. We can even use the smoothing operation along with histogram process for image enhancement. There are two types of smoothing filters. One is the box kernel. The second one is the Gaussian kernel. So, if I have an m cross n size of my kernel and all the coefficients are 1, then we call it as the box kernel. We have a normalizing constant before the box kernel, which is very useful to decrease noise and maintain uniform intensity range. So, as shown here, if I consider my 3x3 box kernel, all my coefficient values are 1, and I have a normalization constant which is given by the sum of the normalizing constant is equal to the average of the coefficients. Okay. If we are considering 3 cross 3, then the average of the coefficient is 9. So the normalizing equation is given by 1 by 9. Now, if I consider 5 cross 5, then my average constant is equal to average value of my coefficient is equal to 25, which implies my averaging constant is 1 by 25. Now, if I have an M cross N kernel, where the coefficients are given by the equation, which is equal to g of s comma t is equal to k into e power minus s square plus t square by 2 into variance square, then that type of a filter or that type of a kernel is called as the Gaussian filter. For 3 cross 3 Gaussian filter, I get my coefficient values from this equation. So, if I consider my box kernel, I can say that the normalization in the kernels is used for constant intensity values for my filtered as well as my original image. To maintain the constant intensity values in filtered as well as my original image, I use my normalization constant. Even for reducing my biasing during my filtering operation. This box kernel is a separable kernel. What do you mean by separable kernel is, if I have my coefficients of my kernel represented by g of x comma y, then I can represent my kernel g of x comma y by two functions g1 of x into g2 of y, then it can be termed as a separable kernel. So I have a 2D function and I am representing my 2D function as multiplication of 1D to 1D functions. Then we call it as a separable kernels. So we are using this box kernel when we want to smoothen our edges. When we come to Gaussian kernel, we don't have any normalization constant. We are not having any normalization constant, and it is a separable kernel. Third point, we are using it to smoothen the whole image. Box kernel is specifically used for smoothing of the edges. When we want to smoothen the whole image, we are using our Gaussian kernel. In our previous example, we have seen here for 3 cross 3, in my Gaussian kernel, my origin of my kernel is 1 and the values are decreasing along the x and y axes. So, my Gaussian filter will have my frequency response as shown here. So, from here we can observe that when we use the Gaussian filter with respect to our image, the origin or the highest point where the kernel is mapped, it is having the highest values and the values are decreasing along the x and y axes. Because of this operation, it is very useful for smoothing of our whole image.
Like, share and subscribe. Hit the bell icon for more updates.